The use of fiber to reinforce concrete is by no means a new technology. However, it is one that is constantly expanding. There are many types of fibers that can be added to concrete to increase its mechanical properties. The main types, and subsequently the types that will be discussed in this following presentation, are steel, polypropylene, glass, and carbon fibers. The behavior of steel fiber reinforced concrete was the primary subject of early theoretical studies of fiber reinforced concrete in the early 1960s. Since then, steel fiber reinforced concrete has become the most commonly used fiber concrete, though it is now becoming less popular to use due to the development of synthetic fiber reinforced concrete. Originally, they were mainly used as a replacement for the secondary reinforcement, often used for crack control in flat slabs, pavement, and repair applications. Today, they are still extensively used for these purposes. They are also used increasingly in structural applications, such as replacing entirely or complementing conventional steel reinforcement. ASTM defines 5 types of steel fibers. All types of fibers should be small enough to be dispersed randomly in a concrete mixture. Depending on the fiber geometry desired, the steels are manufactured in different ways. Smooth surface fibers were originally used in application. They are no longer commonly used as they don't develop the same bonding as steel fibers that have either rough surfaces or ends that are either hooked or enlarged. This is important because the fiber geometry plays an integral role in the efficiency of fibers as the geometry governs the pull-out force and the displacement of fibers during post-cracking behavior. The principal purpose of steel reinforced concrete is to improve the post-peak load carrying capacity of the concrete. Having steel fibers present increases the toughness of cements and concretes. The increase in toughness minimizes cracking due to changes in relative humidity or temperature. It also increases the resistance to dynamic loading, such as those due to fatigue, impact, blast, or seismic events. The improvement in strength due to steel fibers is modest unless there is a high volume of fibers. Similar to the regular steel reinforcement bars, they are less effective under compressive loading. As with any type of concrete mix, proportions depend on workability, strength, durability, and other requirements of the project. Performance of the concrete is enhanced more with a higher volume of fibers. On the other hand, both workability and uniform distribution decrease with increasing fiber length and volume. When mixing the fibers into the concrete, the goal is to have sufficient volume of uniformly dispersed fibers to contribute to the desired mechanical improvements. With the presence of superplasticizers, about 2% of fibers can be incorporated into the practical concrete practice. When steel fibers are introduced into the concrete mix, they generally have a detrimental effect on the packing density of aggregates and fiber clumping occurs. These are main factors in limiting the steel fiber content. The next type of fibers to be discussed are polypropylene fibers. Polypropylene is a pure hydrocarbon that is derived from methylethylene and is a hydrophobic material. There are 3 different types of fibers that are typically used. These 3 types are monofilament, microfilament, and filabrated. Each of these fibers have differing sizes, strengths, and densities. The addition of polypropylene fibers does not alter mix design of concrete. Typical volume percentages used in batches are generally between 0.1 to 0.3%. It is able to be used in such applications as slabs, pavements, beams, etc. The addition of polypropylene fibers increases the compressive strength of concrete. As shown in this figure, the increase in strength is directly proportional to the increase in fiber addition. The addition of these fibers has also been linked to increasing the ductility of concrete specimens. The image on the left displays the failure of a concrete specimen without polypropylene fibers. This represents brittle failure that is undesirable in service. The image on the right displays the failure of a concrete specimen with polypropylene fibers. This represents ductile failure. This is preferred in service as it allows for beams that are failing to be noticed and the opportunity to remedy the issue before failure. The addition of polypropylene fibers can directly benefit the flexural properties of concrete. This benefit is spurred from polypropylene's ability to increase crack resistance. As shown in this figure, the increase is flexural strength is directly proportional to the increase in fiber volume percentage. It was also noted in a study performed at the Harbin Institute of Technology in China that the flexural strength of concrete is able to be further increased by twisting polypropylene fibers. These figures represent the experimental results for polypropylene fibers that are twisted and non-twisted. The figure on the left displays the increase in flexural strength for concrete specimens without twisted fibers, and the figure on the right displays results from specimens with twisted fibers. As you can clearly see, there is a slight increase in strengths when the same proportion of fibers are used, but twisted. The addition of polypropylene fibers has been noted to increase fire resistance of concrete specimens. The loss of concrete's compressive strength is less with the addition of polypropylene fibers after extended exposure to extremely high temperatures. As shown in this figure, it has been noted that an addition of 0.5% fibers has a more positive impact on the compressive strength. This figure is at an extended exposure temperature of 600 degrees Celsius. This 0.5% addition of fibers was noted to decrease the compressive strength by about half, compared to the specimen where no fibers were added. Glass fibers are another common fiber additive to increase generic concrete capabilities. Fibers are created through a melting and extrusion process. Silica is the main fiber component and accounts for roughly 70% of the fiber's chemical composition. Approximately 15% is zirconium, which is added to aid in alkali resistance. The finished fiber product is either a long continuous strand or short discrete fibers. There are two main methods in which the fibers are incorporated into the concrete mixture. The first of these methods is the spray-up method, where the long continuous strands are run through a chopper gun and sprayed into the wet concrete during pouring. The fibers are then rolled into the wet concrete to ensure proper binding and compaction. The second method is known as premixing and is where pre-cut fibers are added to the concrete mixture during batching. The addition of fibers at the concrete batch plant is by far the more common of the two methods. The mechanical properties of glass fibers are highly superior when compared to those of unreinforced concrete. The fiber's higher tensile strength is the most important of these qualities. Glass fibers are typically within the range of 10 to 50 millimeters in length and make up 0.5 to 5% of the concrete mixture by weight. The much larger values of strain and modulus of elasticity contribute to a more ductile concrete to be created, allowing for safer designs and structures to be created. Another added benefit of the addition of glass fibers to concrete is the increase in impact resistance. Studies have shown increases of impact resistance of up to 60% and increases of first and ultimate crack resistance by 5 and 6 times respectively. This high impact resistance makes glass reinforced concrete ideal for applications such as roadside barriers, marine structures, and bomb shelters. Another type of fiber used in reinforcing concrete is carbon fibers. Up until about 10 years ago, there was little research into this topic and it wasn't widely used because of the price of carbon fibers. However, in recent years, due to improvements in the carbon fiber manufacturing process, there has been a large decrease in cost, making them a more viable option for reinforcing concrete. On the slide, you can see two main types of fibers. Non-continuous fibers refer to short fibers, often 5 to 10 millimeters in length, while continuous fibers generally have one very long fiber strung throughout the mix. Continuous fibers have been found to provide better strength. However, they are much more expensive and time-consuming as they have to be manually put into concrete forms. Thus, continuous fibers are not used as commonly as short fibers. The tensile strength of concrete is very weak, often found to be only 10 to 15% of a concrete's compressive strength, thus making it very weak in flexure and susceptible to cracking. On the other hand, carbon fibers are extremely strong in tension, making them very beneficial when reinforcing concrete. A study performed at the University of South Korea found that when percent volumes of up to 3% were used in concrete mixes, gains of up to 100% were seen in the cement mortar's tensile strength. Ductility is also extremely important in a structure to show signs of fatigue before a failure which endangers human life. Concrete is typically a very brittle material, but the addition of carbon fibers, which have a large elastic modulus, can often give the concrete more ductile properties, which can help with resisting seismic and dynamic loads often experienced by buildings. A study found that between unreinforced concrete, carbon fiber reinforced, and steel fiber reinforced concrete, that carbon fiber reinforced concrete gave the best results of dynamic properties, as can be seen in the table on the slide. One of the main causes of concrete failing is corrosion of the steel reinforcement used to provide tensile strength. The use of carbon fibers with reinforcing steel has been found to increase corrosion in steel because it reduces the electrical resistance per unit volume, thus allowing electrons to flow more freely through the concrete. While this is bad for the concrete, the effect can easily be reversed by adding silica fume to the mix. Due to this, it is believed the positives of carbon fibers far outweigh the negatives. After review of these various fiber types, it can be easily asserted that fiber addition to concrete is beneficial in almost all areas. No single fiber can be chosen as a superior addition due to the aforementioned strengths and weaknesses.